When a patient with advanced cancer enters palliative care, oncologists must evaluate their prognosis across three highly distinct timelines: short-term, meaning 3 weeks or less, mid-term, from 24 to 52 weeks, and long-term, surviving over a year. If a patient is in their final weeks of life, a full regimen of radiation therapy introduces severe physical strain. The side effects and clinical visits consume the tiny fraction of time they have remaining, adding discomfort rather than relieving it. Yet for patients whose survival stretches into months or years, that same palliative radiotherapy is incredibly effective. It shrinks tumors, stops bleeding, and provides immense relief from debilitating bone pain. This creates a difficult clinical paradox. The decision to initiate active radiation treatment or to pivot strictly to basic supportive care rests entirely on predicting exactly how long that patient will live. Physicians typically rely on their own clinical observation to estimate this timeline, but human intuition in these complex cases is notoriously imprecise. Developing highly accurate, data-driven prognostic tools is a necessary step to prevent unnecessary human suffering. Machine learning excels at this exact type of problem. It can ingest massive amounts of patient data to detect hidden prognostic patterns that a human observer would miss. But standard models, particularly deep neural networks, suffer from a black box problem. An algorithm might output a highly accurate life or death recommendation, but it obscures the mathematical pathways it used to get there. In oncology, doctors cannot act on a recommendation they cannot verify. A 2026 secondary analysis of the International PRAISE trial addressed this exact barrier. Researchers analyzed data from 573 patients receiving palliative radiotherapy for bone metastases. To process the 65 distinct clinical, biological, and treatment variables collected for each patient, the researchers deployed a decision tree multi-class classifier. This specific model architecture natively outputs its logic into a readable hierarchy. By presenting a visible, rule-based logic structure, the algorithm allows oncologists to trace the reasoning step by step. It provides the required transparency for actual clinical adoption. This decision tree maps the patient cohort into 4 precise classification endpoints based on overall survival time. These range from Class 0, indicating mortality within 3 weeks, all the way to Class 3, marking survival beyond 52 weeks. At the top of the diagram is Node 0. This represents the entire initial group of 573 advanced cancer patients before any algorithmic sorting occurs. For its first and most crucial sorting criterion, the model bypassed traditional clinical metrics entirely. It split the patients based on a laboratory biomarker, the concentration of interleukin-8, or IL-8, in their blood. Moving down to Node 3 shows the impact of this split. The algorithm isolated patients with the highest IL-8 levels, revealing that the vast majority in this subset fell into Class 0, surviving for less than 3 weeks. Over at Node 1, the inverse is true. By filtering for the lowest IL-8 levels, the model isolated a subgroup with a 92% probability of surviving well past a year. A single objective biomarker can bypass subjective physician estimates, accurately mapping the extreme upper and lower bounds of a patient's expected survival. The model's reliance on a blood marker raises a mathematical question. Out of 65 possible clinical and laboratory variables, how did the algorithm know to select IL-8 first? To determine the optimal variable for each split, the researchers trained the decision trees using 2 different mathematical criteria: entropy and Gini impurity. Entropy is a metric that focuses on information gain. The algorithm calculates the formula to minimize the randomness of the data, actively seeking to carve the patients into subsets that are as homogeneous as possible. Gini impurity, on the other hand, calculates the exact probability that a randomly chosen patient within a node will be misclassified. The lower the Gini value, the higher the purity of that category. The decision tree operates recursively. At every node, it tests all 65 variables across every possible numerical threshold, searching for the precise split that minimizes the Gini index and maximizes accuracy. Upon testing, the researchers found that the model using the Gini-based approach yielded superior predictive performance across the patient data compared to the entropy method. By rigorously optimizing for category purity at every individual split, the algorithm generates a definitive, mathematically sound branching structure that clinicians can actually trust. To quantify the exact weight each variable carried across the entire model, the researchers applied SHAP values, which stands for Shapley Additive Explanations. The concept originates in game theory. It measures an individual player's, or in this case, a single variable's, marginal contribution to a collaborative team effort predicting a final outcome. This SHAP summary chart visualizes those contributions for the Gini model. It highlights the dominance of 3 specific laboratory variables: interleukin-8, lymphocytes, and hemoglobin. Looking at the multicolored bars representing the 4 survival classes, these 3 top factors account for over 80% of the model's total predictive power. You can contrast this massive data footprint with the traditional clinical metrics at the bottom of the chart. Factors like patient performance status, recent food intake, and steroid use exert remarkably little influence on the model's final predictions. The algorithm exposes a shift in how survival should be evaluated. Accurate prognostication relies heavily on objective blood chemistry over subjective physical observation. These strip plots show the raw biological data distribution of the patient cohort, allowing us to verify the machine learning model's mathematical conclusions directly against the reality of the trial. The first plot shows a stark inverse correlation. Interleukin-8 values are exceptionally high for the short-term survival group in Class 0, and they plummet as patient survival times increase toward Class 3. The middle and right plots track hemoglobin and lymphocyte counts. Both behave exactly opposite to IL-8. Their values scale directly upward as patient survival windows lengthen. These distinct class separations carry a high statistical significance, with p-values less than 0.0001. This confirms that the model's priorities are grounded in core biological realities rather than algorithmic anomalies. Explainable AI is only clinically viable when its internal mathematical abstractions precisely mirror verifiable human biology. To evaluate the multi-class model's overall accuracy, the researchers utilized receiver operating characteristic curves, evaluating the area under the curve, or AUC, for each specific timeframe. This chart shows the model's testing set performance. It displays excellent discrimination capability at the extremes, accurately isolating the rapid mortality cohort with an AUC of 0.80 and the long-term survival cohort at 0.78. However, tracing the blue curve reveals the model's severe predictive blind spot. Accuracy collapses almost entirely for Class 2, which represents the 24 to 52-week survival window. An AUC score near 0.5 means the model is mathematically providing absolutely no discriminative advantage over a random guess for this specific timeframe. The clinical implication is that midterm survival is likely governed by highly complex, nonlinear biological factors. The current routine biomarkers are simply failing to capture the full picture of a patient's decline at that specific stage. Transparency in AI is vital exactly for this reason. By exposing its own limitations, the model prevents physicians from blindly trusting algorithms in the precise areas where they mathematically fail. Returning to the complete decision tree, we can trace the optimal survival pathway identified by the algorithm, filtering down from node 0 to node 1 and ending at node 5. At node 5, the data shows that the combination of low interleukin-8 with high lymphocyte counts ensures a greater than 90% probability of a patient surviving past a year. Handing this interpretable, visual tool directly to a radiation oncologist during a patient consultation changes the nature of the conversation. The model delineates precisely who will benefit from targeted radiation to relieve their pain, and who must be spared the physical toll of treatment in favor of immediate, focused supportive care. By combining objective laboratory biomarkers with transparent algorithmic logic, medical physics provides a humane, deeply actionable map for the hardest decisions in end-of-life care. To evaluate the multi-class model's overall accuracy, the researchers utilized receiver operating characteristic curves, evaluating the area under the curve, or AUC, for each specific timeframe. This chart displays excellent discrimination at the extremes, accurately isolating the rapid mortality cohort with an AUC of 0.80 and the long-term survival cohort at 0.78. But tracing the blue curve reveals a severe blind spot. Accuracy collapses entirely for Class 2, the 24 to 52-week window, An AUC score near 0.5 means the model is mathematically providing absolutely no discriminative advantage over a random guess for this specific timeframe. The clinical implication is that midterm survival is likely governed by highly complex, nonlinear biological factors. The current routine biomarkers are simply failing to capture the full picture of a patient's decline at that specific stage. Transparency in AI is vital exactly for this reason. By exposing its own limitations, the model prevents physicians from blindly trusting algorithms in the precise areas where they mathematically fail. Returning to the decision tree, we trace the optimal survival pathway filtering from node 0 to node 1, ending at node 5. Here, low interleukin-8 combined with high lymphocyte counts ensures a greater than 90% probability of surviving past a year. Handing this interpretable, visual tool directly to a radiation oncologist during a patient consultation changes the nature of the conversation. The model delineates precisely who will benefit from targeted radiation to relieve their pain, and who must be spared the physical toll of treatment in favor of immediate, focused supportive care. By combining objective laboratory biomarkers with transparent algorithmic logic, medical physics provides a humane, deeply actionable map for the hardest decisions in end-of-life care.